Hello. So we have discussed the Clausius inequality and the mathematical statement of the second law of thermodynamics in our previous sessions. I hope doing a numerical problem will give more clarity to the equations that is involved. So here is a sample problem. This is a problem. A heat engine receives 100 kilocalorie of heat from a source at 1000 Kelvin. It rejects 50 kilocalorie. Another option is 75 kilocalorie, and the third case is 25 kilocalorie of heat to the surroundings, which is at 500 Kelvin. Investigate the nature of the process in each case. So this is the problem that is given to us. So it's a hypothetical, it's a engine that is reported, or we are designing an engine in such a way. Okay, so let's analyze whether this heat engine can perform the operation in the manner in which it is designed. Okay, so or is there any restrictions on its working? So in order to do this one, you can just verify whether these values are satisfying the Clausius inequality, or whether it is obeying or just following the second law of thermodynamics. So so far in the Kelvin-Planck statement and the Clausius statement, which I told you are the two wordly statements of the second law of thermodynamics, we cannot actually see anything that is forbidden in all these three cases, because you can see if you analyze this problem, in all the cases there is a high temperature reservoir. Actually I should have used three different engines, but for sake of simplicity and convenience I have used the common reservoir for all the three different engines. But see, you consider that these are our three different engines. It's only to aid your understanding of the problem. This diagram is only optional. So the high temperature reservoir is 1000 Kelvin, and the low temperature reservoir is having a temperature 500 Kelvin. So you can see automatically such a design is possible. Okay, if you look at the spontaneous direction of flow, and or heat can flow from higher temperature to low temperature. But the thing is that you have to check whether these values are permitted. Okay, so let's check it. Okay, so a heat engine receives 100 kilocalorie of heat from the source. So in each of these cases the heat received is the same, that is to be noted. So 100, and we say that here it is 100 kilocalorie, whatever unit doesn't matter, 100 joules also you can take it. Okay, so 100 kilocalorie. See that all these cases the engine is taking the same amount of heat from the high temperature reservoir, and the cases one by one it rejects. In the first case it is designed to reject how much? 50 kilocalorie. 50 kilocalorie. And the second case, in the second design of the same heat engine, it is just 75 kilocalorie. It is rejecting this much. And the third design, it says that it is rejecting 25 kilocalorie. Seemingly you will see that these things are not having any problem, but let's check it. How to check whether this one can happen or not? So the Clausius inequality comes to our help here. So let's see how to do that one. So what we will do is that we will calculate the value of the Clausius inequality in each of these three different cases. Okay, so case 1, right? Reference diagram is on the other side. So let's evaluate this integral, Clausius integral. So what is that? Closed integral of d bar q over t for the cycle. You know, a heat engine schematic diagram represents a complete cycle, right? D bar q over t. So let's do it for the first case, first design. So what is that? You know what to do. You have to take the heat entering the system. Here is what heat entering. What is heat entering the system? 1000 kilocalorie. Sorry, 100 kilocalorie in each case, divided by the temperature at which the heat is entering the system. That is assumed to be 1000 Kelvin, right? So we'll calculate it this way. 1000, sorry, heat entering, no, QH by TH, okay, minus QL by TL. That is what you have to do. Okay, so it is 100 divided by TH. What is that temperature of the temperature which is here? It is 1000. Only the thing to be taken care is that this temperature should be in absolute scale. Heat can be in any units, but the temperature should be in absolute scale. Okay, minus the QL by TL. That is what you do in a cycle. QL is 50 kilocalorie. 50 by TL. TL is what? Temperature at which the heat is lost or rejected. That is 500 Kelvin. Okay, by 500. Okay. Of course, the unit will not be joule per Kelvin. Instead, it will be kilocalorie per Kelvin. Okay. Don't worry about the unit of this one. Kilocalorie per Kelvin. That will be the unit. So, what about this value? Let's calculate this value. That is equal to 100 by 1000 is nothing but 0.1, right? So, this is 0.1 minus, what is the 50 by 500? Of course, 50 by 500. Anyway, it will be less than that, right? So, it will be just 0.1, right? Again, 0.1. Okay. So, 0.1 minus 0.1, okay, that is equal to 0. So, this particular case number 1, gives the closed integral d bar q over t is equal to 0. Hope you can recall what is this one. It corresponds to the reversible part of the second law of thermodynamics. So it says that these changes are these changes are reversible in nature. So it corresponds to a data for a reversible in nature. Okay, this is possible. It is okay permitted. That is, it's a just a permitted design, right? So that is what we conclude. These are reversible in nature. So we are asked to investigate the nature of the process. So we have investigated, and we have found that from this value of this integral that this process is reversible in nature. That is the thing, reversible process. So same manner you can just do the second case. The second case also you evaluate the same integral. So cyclic integral of d bar q over t. It's equal to, once again, the same manner. So consider this one. So what is the equation? QH by TH, right? So it is again, this value is same, 100 by 1000 minus, why this minus? I think I understand why this minus. As far as the system is concerned, remember always this circle denotes the system, okay, and this is the surrounding. Hope you remember that in the case of terminologies used, usually the surrounding is nothing but the low temperature reservoir. Okay, for as far as a real heat engine is concerned, the low temperature reservoir is nothing but the surrounding or to the air, external atmosphere. Usually it is at 300 Kelvin, room temperature. But in this particular example, it is given 500 Kelvin. Let's accept it. Okay, so this is system. So we always talk about the heat entering the system, which is 100 kilocalorie. At what temperature? At 1000 Kelvin. Okay, and the heat leaves the system at 500 Kelvin. Okay, that's what we usually imagine. Okay, see, that's the thing. So heat leaving the system should be taken as negative. That's why we are putting a negative here. Okay, so hope you remember the theory that we have discussed in the previous session. So the second one, minus, what is the heat leaving? That is 75. Minus 75 upon, what is the temperature? Again, that is 500. 75 by 500. One thing is for sure. What is that? This value will be equal to, what is this value is going to be? That much, of course, the same units, kilocalorie per Kelvin, whatever it is, okay, or joule per Kelvin. So this is once again is going to be 0.1 minus, what is 75 by this one? So 50 by 500 was 0.1. So 75 by 500 should be 0.15. Am I right? 0.15. You can check it. 0.15. So that much thing. And this is, that's going to be minus 0.05 kilocalorie per Kelvin. That's going to be, and you note this negative sign. What does it mean? This integral, so corresponding I can say that this integral d bar q over t is what? Less than 0. And what is your conclusion? The conclusion is that this is also permitted by whom? By the Clausius inequality. The first one is the Clausius theorem permission, and the second one is the Clausius inequality permission. Means the changes, the process here or the changes here happening here in this case number 2, the process is irreversible in nature. Process is irreversible in nature. So we could investigate. So both cases 1 and 2 are permitted by the second law of thermodynamics. So out of curiosity, let's go to the third case. I think automatically it comes to you what is going to happen now. In the third case, integral d bar q over t, right? That will be equal to, same manner you evaluate it for the incoming heat. What is that? 100 kilocalorie at a temperature 1000. So it's all same in all the three cases. So only to make our calculation easy, it has been done like this: 1000 minus, right? Second part, what is the heat outgoing rejected? That is 25. That is 25 upon 500. 25 upon 500. What is going to happen? This is equal to some 0.1 minus, what will be 25 by 500? So won't it be 25 by 500? It's going to be 500 by 80. Yeah, so that is going to be 0.05. 0.05. Is it not? 0. Yeah, it's 0.05. So that will be equal to 0.1 minus 0.05 is plus 0.05. You note the second and third examples. There's a little bit of difference. Kilocalorie, whatever units per Kelvin. Okay, you note one thing. That is the integral, the cyclic integral of d bar q over t for the third design of this engine is positive, greater than 0. What about this particular thing? This is about what I have cautioned you earlier, or what Clausius inequality do not hold good. So it means that this particular case or this particular design of the engine can never happen. So this process can never happen. Okay, it can never happen, or it is forbidden by the second law. Forbidden by the second law. And this is exactly what is the use of Clausius inequality, or both that equation. So remember always, once again I remind you, the Clausius statement of the mathematical statement of the second law of thermodynamics is closed integral of d bar q over t should be either less than 0 or equal to 0. And this is the mathematical statement of the second law of thermodynamics. Okay, so that helps us to ascertain, to determine whether a given design of a process, be it a heat engine or it is a refrigerator. Yeah, that I forgot to tell you. See, we did all the proof for a heat engine. Whatever proof we have done, Clausius inequality or the Clausius theorem, whatever proof we have done for a heat engine is equally applicable for the refrigerator as well. Okay, for the refrigerator also this is correct. So you can just try it out. So it won't give you any difference in the thing. So this is true for any process. Okay, so whether or not a process will be permitted, will occur in nature, can be decided based on the Clausius inequality and the Clausius equality. Okay, and that is the importance of this particular case statements. Hope that gives you some clarity on what we have been doing. Try to do more problems. Okay, you can refer to any of the reference textbooks or any websites or anything. and try to do more problem. That is a way to get clarity on all these symbols. You will become more experienced with, or more acquainted with all these symbols. Okay.